Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss fired heaters, fire and flue gas side draft and afterburn, and how to optimize excess air. Next to the efficiency of the trays in a distillation tower, the efficiency of a fired heater is the most critical factor in saving and/or making money for the process plant. The primary objectives in operation of a fired heater are to keep the fire in the firebox. Avoid excessive heat density in the firebox. Maximize the process heat absorption for a given amount of fuel. These objectives are equally important in the operation of fired boilers, whose principles of operation on the fire side and flue gas side are essentially the same as those of process plant fired heaters. The two governing modes of heat transfer in the construction of a fired heater are radiation and convection. In the firebox, heat transfer by radiation reigns supreme, governed by Lambert's laws, as follows. QR equals a epsilon T power for FB minus T power for Tm, where QR equals radiant heat transfer rate, BTU per hour. A equals surface area of the radiant tubes in the firebox, square feet. Epsilon equals emissivity factor. TFB equals absolute temperature, degree Rankine, of the radiant surface, which is essentially the firebox temperature. The reason for this is that the flames heat not so much the tubes as the refractory, and the refractory then re-radiates the heat to the tubes, so the main heat source becomes the refractory. TTM equals the receiving metal absolute temperature, degree Rankine. This is the radiant tube metal or tube skin temperature. Rankine equals degree F plus 460. The amount of heat transferred to the process fluid in the convective section of a heater is governed by QC equals A times U, TFG minus bulk, where QC equals convective heat transfer rate, BTU per hour. A equals surface area of the tubes, square feet. U equals a heat transfer coefficient, BTU per hour square feet, degree F. TFG equals temperature of the flue gas, degree F. Bulk equals temperature of the process fluid flowing inside the tubes, degree F. Note that the temperature driving force for radiant heat transfer, TFB power 4 minus TTM power 4, is always a very large number as compared to the temperature driving force for convective heat transfer, TFG minus bulk. For this reason, in non-fouling services we use fin tubes in the convective section of our fired heaters to increase the surface area of the tubes. The tubes in the firebox or radiant section are made of high-chrome steel capable of withstanding firebox temperatures of up to 2000 degrees Fahrenheit, depending on the severity of operation for which the heater has been designed. Some very high-severity heaters may be designed for firebox temperatures of greater than 2000 degrees Fahrenheit. Note especially that radiant section tubes are protected from overheating by the cooling effect of the process fluid flowing inside them, where flowing is the key word. The bare, unfinned, shot tubes are also cooled by the process fluid flow shown in picture. However, the convective section fin tubes are not intended or designed to withstand such high temperatures, and so the tubes themselves are often made from low-temperature rated carbon steel. The fins, which are not cooled by the process flow, are made from chrome steel. As it is much easier to make fin tubes from just one type of metal instead of two, though, the furnace manufacturers will often choose to make the fin convective section tubes entirely out of low chrome steel, in which case one could expect them to withstand temperatures of less than or equal to 1300 degrees Fahrenheit. It is advisable to check what types of tubes you have in your furnace and know what temperature tolerances they have. The only thing that prevents the tubes in the convective section from overheating up to firebox temperatures is that we keep the fire in the firebox and do not allow the fire to get up into the convective section. This may sound obvious, but it is surprising how many people seem to forget or ignore this fact. Effect of reduced air. Flow. A typical natural draft gas fired process heater is shown in picture. Suppose we gradually close either the stack damper or the air register. The flow of air into the firebox will then be reduced. If both the process side flow and the fuel gas rate are held constant, the following sequence of events occurs. 1. The heater process outlet temperature begins to increase as the excess air is reduced. This is because more heat is given to the process fluid and less heat goes up the stack. 2. The heater process outlet temperature declines as airflow is reduced past the point of absolute combustion as defined in the next section. In this situation we have products of incomplete or partial combustion, such as aldehydes, ketones, and carbon monoxide going up the stack. This sets the heater up for afterburn in the stack, and the heating value of the fuel is also effectively reduced. Allowing a fired heater, boiler, or furnace to operate with insufficient air is hazardous because the products of incomplete combustion are hot and will ignite as soon as they find sufficient oxygen. This usually results in afterburn in the convective section or stack and can even lead to explosive detonations. The products of partial combustion are atmospheric pollutants. It is not possible to operate an automatic temperature control on the wrong side of the point of absolute combustion. Absolute combustion. Consider a forced draft boiler producing 600 psig steam as shown in picture. The fuel rate on this boiler is fixed and we are going to optimize the oxygen, O2, content of the flue gas by adjusting the speed of the forced draft, FD, fan. Do we simply adjust the FD fan to give 2% O2 in the stack because someone once said that 2% O2 in the stack was a good number? No. We are going to adjust the speed of the FD fan to produce the maximum amount of 600 psig steam. In other words, we are going to maximize the heat to the process by adjusting the air rate. The point at which the steam production is at maximum is the point of absolute combustion. The oxygen content of the flue gas at the point of absolute combustion, where steam production is maximum for a given amount of fuel, will be the optimum. It will not necessarily be at 2% O2 or any other fixed oxygen content. The oxygen content of the flue gas at the point of absolute combustion is a variable, depending on air-fuel mixing efficiency. The term absolute combustion is not the same as complete combustion. Complete combustion is a theoretical term, implying a theoretical goal that we might aim toward but will never quite reach on any real process heater or boiler. The point of absolute combustion represents the best achievable efficiency point of any such piece of equipment on any day of the week, at any hour or minute. One definition of the point of absolute combustion is the point of maximum heater outlet temperature for a given amount of fuel as illustrated in picture. Following this, we can say that the point of absolute combustion is also the point of best or maximum achievable combustion for a given amount of fuel as illustrated by picture. The point of absolute combustion in terms of either maximum heater outlet temperature or minimum fuel fired for a given outlet temperature would correspond to the same flue gas oxygen content for a given furnace at the same moment in time. However, we must also note that this flue gas oxygen content that corresponded to the point of absolute combustion on, say, heater 3304A on Monday, January 2, 2023, at midday is not likely to correspond to the point of absolute combustion on the same heater on Tuesday, January 3, 2023, at midday, or even Tuesday, January 2, 1996, 1 hour or 1 minute after it was first determined. Indeed, the oxygen content, %O2, of the flue gas typically varies in the range of 0.5% O2 to as much as 10% O2 depending on the design, mechanical integrity, and operating characteristics of the equipment, such as firing rate, burner type, and ambient weather conditions. Did the oxygen analyzer really help us find the point of absolute combustion for the forced draft boiler? No, it did not. However, once you have found the point of absolute combustion and then noted the corresponding flue gas %O2, as long as all operating conditions remain constant for the heater, then you could use the %O2 in the flue gas as a rather secondary guideline for that period of time until the operating conditions changed. Oxygen starvation. If you try to operate a fired heater with too little combustion air, you will starve the burners of oxygen to smother or bog down the firebox. Then you will likely cause afterburn or secondary combustion in the stack. You will not be able to operate on automatic temperature control, and you may even destroy the equipment altogether. This type of operation can also be described as operating on the wrong side of the point of absolute combustion. Take another look at pictures. We are talking here about the portion of the curves marked as bad operation. What would be the color of the flue gas as it emerged from the stack during this type of operation? Would it be black? No, it would not necessarily be black. If we were burning heavy industrial fuel oil with a very high carbon-hydrogen ratio, then yes, very soon after we began to operate on the wrong side of the point of absolute combustion, the stack gases would turn black. After all, the black color is merely soot or unburned carbon. However, if we were burning pure hydrogen, the stack gases would never turn black no matter how much we starved the firebox of oxygen. If we were burning natural gas, then as we crossed over the wrong side of the point of absolute combustion, we might initially just be able to see the stack gases turn only a pale yellow. If we continued to decrease the combustion air rate, the stack gas color might progress from pale yellow to dark yellow, to light orange, to dark orange, to brown, and finally to black. The color of the stack gases is not an accurate indication of whether we are using enough combustion air, as the point at which the stack gases finally turn black depends on the carbon-hydrogen ratio of the fuel. Also, while continuing to fall below the point of absolute combustion, we accelerate the production of atmospheric pollutants such as aldehydes, ketones, light alcohols, carbon monoxide, and other products of the partial combustion of light hydrocarbons in the stack gases. If we have the furnace on automatic temperature control while we are not using enough combustion air, and if the control valve on the fuel gas then opens to allow more fuel to the burners in order to increase the furnace outlet temperature, the extra fuel will not burn efficiently. In fact, the extra fuel is likely to reduce the heater outlet temperature rather than increase it, as there is already a shortage of air, and it cannot burn properly and tends to cool the firebox. The automatic temperature controller then senses the reduction in heater outlet temperature and increases the fuel rate. Thus, the furnace will spiral into an increasingly dangerous condition as the outlet temperature continues to fall and the furnace is left on automatic control. The way out of this situation is to put the furnace on manual control and manually reduce the fuel gas back to the point of absolute combustion. To determine if you are running above the point of absolute combustion, that is, the safe area, observe the heater outlet temperature as you manually reduce the fuel gas rate. If this temperature increases, then you are still on the wrong side of the point of absolute combustion. If this temperature decreases, then you are on the safe side of the point of absolute combustion. Do not open the burner air registers until you are on this safe side. Increasing airflow when operating in a fuel-rich environment may make the firebox explode. However, if we operate on manual without enough combustion air, we will share the experience explained by one oil refinery operator as follows: our crude unit heater is very old, we have to operate it manually. We have 3 air blowers to produce the combustion air, we always run 2 with 1 on standby. Once a week we switch the blowers by shutting one down and turning on the one that was idle. One week I was switching the blowers when I forgot to shut one of the 2 down before starting up the 3rd blower. I then had all 3 blowers running at once. Our normal heater outlet temperature target is 680 degrees Fahrenheit, but while I had all 3 blowers on, the outlet temperature rose rapidly to 740 degrees Fahrenheit. Rather than cutting the fuel gas back to reach a 680 degrees Fahrenheit outlet temperature increasing excess oxygen, he shut down the 3rd blower and dropped the furnace temperature back to 680 degrees Fahrenheit, but also continued to run fuel-rich, without enough air. Which is cheaper, air or fuel? Of course, the answer is air. Are we trying to make the flue gas to some particular oxygen content specification, or are we trying to save fuel? Certainly, the answer is that we want to get the most heat we can out of every pound of fuel. Well, then, dear viewer, let us neither set nor encourage the use of these stack or flue gas oxygen targets. They are meaningless and often cause more harm than good. Appearance of the firebox and flames. Regardless of and in preference to oxygen analyzer results, we must consider the appearance of the firebox and flames when we assess whether more combustion air is needed. If the firebox appears bright and clear, then there is more than enough oxygen. A crystal clear firebox has a large excess of oxygen. If the firebox appears hazy and the flames are long, licking, yellow, and smoky looking, then there is not enough oxygen. To be just right, the firebox should have a very slight haze and all the flames should be compact and not searching around the firebox looking for oxygen. Do not stand directly in front of an inspection port while you open it, in case there is positive pressure behind it. Flame color depends on fuel composition. Gas often burns blue, but heavy fuel oil burns yellow. A yellow flame is caused by thermal cracking of the fuel. There is nothing wrong with a yellow flame, it is the general shape of the flame that is important. Flames should be short and bright. The temperature of the inside of a firebox can also be estimated by its visual appearance shown in table. Secondary combustion or afterburn. In the preceding paragraphs we discussed how operation without enough combustion air on the wrong side of the point of absolute combustion leads to inefficient combustion of fuel. Apart from the fuel wastage, there is another important disturbing and frequently occurring problem associated with this bad mode of operation. The products of incomplete combustion of the fuel, and in more severe cases even the unburned fuel itself, flow with the flue gas up through the convective section and up the stack. A certain amount of air leaks in through the convective section and stack from outside the heater. When these hot, combustible hydrocarbons in the form of unburned fuel mix with the extra air that is leaking in from the environment, reignition is liable to occur. We call this afterburn, or secondary ignition, meaning there is now fire in the convective section. When combustible materials or unburned fuel reignite in the convective section, a dramatic increase in flue gas temperature will occur. The metallurgy of thinned carbon steel convective section tubes is not designed to withstand high temperatures. The fins will become oxidized and, when cool, may become brittle and thicker than before, thus restricting flue gas flow. The convective section tubes themselves will become warped and bent and thus restrict flue gas flow still further. Just such a thing happened as a result of another well-intentioned but misguided attempt to improve fuel firing efficiency by reducing the oxygen content of flue gas in a fired heater. This heater, which was also manually operated, had an oxygen analyzer probe installed in the convective section. The operators were given a target range to run between 2 and 6% O2. Note that this range would in many cases actually include the point of absolute combustion. The inside operator, Operator A, noting that the stack gases had 8% O2, began to cut back on the combustion air. As Operator A pinched back on the air register, the convective section oxygen dropped slowly from 8 to 7.5% O2. The outside operator, Operator B, went to check on the firebox and, seeing that it was full of long, licking, yellow, smoky flames and had taken on a very hazy appearance, reported back to Operator A that he considered the amount of air in the firebox was insufficient. Meanwhile, Operator A looked again at his O2 analyzer output, which showed 7.5% O2. He told Operator B that there was plenty of oxygen because the analyzer showed 7.5% O2, so he must be mistaken and, in fact, that he needed to go and pinch back still further on the air register to cut back the combustion air. After cutting back on the air registers, Operator A noticed that the heater outlet temperature dropped, so he raised the fuel rate to maintain the heater outlet temperature. He did not realize that this sequence of events was an indication of insufficient combustion air, because the convective section oxygen analyzer still showed 7% O2, so he asked Operator B to pinch back still further on the air registers. At this point, black smoke started coming out of the stack, and several of Operator B's colleagues began to suggest that they should start to open up the air registers and increase the combustion air and not reduce it any further. However, Operator A, now reading 6.5% O2 in the convective section on his O2 analyzer, was determined to reach his 6% O2, and requested a further cut back on the combustion air. When the combustion air was cut back this time, fire started to come out of the stack. Now Operator A was forced to admit that they would have to increase the combustion air again. The problem they then faced was that the amount of draft in the heater seemed to be less than before and they were not quite able to re-establish the same airflow. The reason for the restricted airflow was that they had caused afterburn in the convective section and damaged the convective section tubes, which now restricted the flow of flue gas and hence the flow of combustion air to the burners. Using the concept of absolute combustion in operations. The only correct oxygen target is that firebox oxygen content that maximizes the process side heat absorption for a given amount of fuel, or if you prefer, we could say it is that the firebox oxygen target that minimizes fuel consumption for a given process side heat absorption. This correct percent O2 in the firebox can be determined only by experimenting with the fired heater, furnace, or boiler in the field. This firebox O2 will also vary for any given piece of fired equipment depending on a variety of factors, including mechanical integrity and firing rate. In reality, it is not the firebox oxygen content that we are looking for so much as the correct combustion air rate for proper operation. The search for the correct combustion air rate on any particular day is known as heat-proving the heater. Experienced operators will increase and decrease the combustion air to find that particular rate that minimizes the fuel rate. Naturally, experienced operators have been heat-proving heaters since long before oxygen analyzers were invented. In view of this, it seems that we do not actually need an oxygen analyzer to run a piece of fired equipment efficiently. The concept is not to run the fired equipment to a specific oxygen target because the oxygen content corresponding to the most efficient operation varies, but to aim instead to maximize heat absorption to the process stream for a given fuel rate. Once we have heat-proved the heater and found this point of maximum heat absorption, which we call the point of absolute combustion, we will then need to operate the furnace with somewhat more air. We call this operating on the good side of the point of absolute combustion, as shown in pictures. If we do not ensure that we operate some extra air to put us on the good side of the point of absolute combustion, then we run the risk of getting into oxygen starvation on the wrong side or bad side of the point of absolute combustion. Automatic operation linked to process outlet temperature while on the bad side of absolute combustion is potentially hazardous because the heater outlet temperature will drop as a result of the reduced heating efficiency of the fuel. The automatic control will then call for more fuel, which, in turn, produces more oxygen starvation. The only way out of this situation is to put the furnace back to manual operation and manually reduce the fuel to get back to the good side of the point of absolute combustion. Note that combustion air is inexpensive compared to fuel. It is irrational to cut back on combustion air and waste fuel by inefficient burning. Also note that to operate fired equipment efficiently, we need to heat-prove it or test to find the point of absolute combustion on a regular basis. Flue gas oxygen and tramp air. Suppose we have a natural draft heater operating very efficiently on the good side of the point of absolute combustion. The oxygen content of the firebox gases, just below the shock tubes, is 2.5% oxygen as shown in picture. What do you think the oxygen content of the flue gases in the stack will be? The answer is it will always be more than the firebox oxygen content, because there are always air leaks in the convective section and stack that, with the slightest negative pressure in the stack or convective section, will allow air to leak in. These air leaks are collectively known as tramp air. The amount of tramp air will vary according to the mechanical integrity of the heater, the number of holes in the casing, the firing rate and draft balance of the heater. The oxygen measured in the stack is the sum of the unused oxygen from the firebox plus the oxygen from tramp air drawn into the convective section and stack. We have already shown that it is wrong to operate a furnace to an arbitrary oxygen target. It is entirely incorrect to adjust the furnace combustion air based on stack gas and/or convective section flue gas oxygen readings, because as a result of the inevitable air in leakage, the stack gas and/or convective section flue gas oxygen content does not necessarily represent the amount of oxygen in the firebox. It is also impossible to offset the stack or convective section oxygen readings to represent the firebox oxygen content because the amount of air in leakage varies so much with time as conditions change. Unfortunately, many heaters have oxygen sensors in the stack and not in the firebox. An oxygen sensor in the firebox may provide a useful guide, as we mentioned earlier, although it is not actually needed to run the heater efficiently. However, an oxygen analyzer in the stack or convective section is really useful only in operations if there is also an oxygen analyzer in the firebox. In such instances, it could be used to trend air leaks across the convective section. Never ever use an online analyzer for technical analysis or test work. Oxygen content field measurements should always be taken with a single portable oxygen analyzer. Be careful to calibrate the portable instrument for the range in which we want to use it. Cylinders of test gases with specific oxygen contents are available for calibration purposes. If the combustion of airflow is being adjusted on the basis of the oxygen content of the stack or convective section gases, that is, from readings taken on an oxygen analyzer with a probe located in the stack or convective section, there may be afterburn or secondary ignition in the convective section. The fire is supposed to be contained within the firebox, and not in the convective section. If we intend to install an oxygen analyzer, the analyzer should be monitoring oxygen in the firebox itself. Lone oxygen analyzers monitoring oxygen in the convective section are misleading as a result of the tramp air and are a positive hazard to safe operation. Draft readings. Draft readings are a comparison of two pressures taken at the same elevation and are traditionally quoted in inches of water. To make sense of a set of draft readings for a furnace, you must first normalize the data. In picture, we see a simple natural draft heater with no convective section tubes. The laws of hydraulics tell us that fluids flow from regions of high pressure to regions of lower pressure, and yet the draft readings in picture seem to contradict this principle. Notice that the draft readings are made at different elevations. Each measurement is in reality a comparison between the densities of the gas both inside and outside the furnace at a given elevation. The temperature difference is the main reason for difference in density inside and outside the furnace. The molecular weights of the furnace gases and of air are approximately the same. To make sense of the draft measurements so that we can use them to evaluate furnace pressure drop, proceed as follows. 1. Make a datum line across the top of the stack as shown in picture. 2. For each draft reading, add on the pressure exerted by the appropriate static head of air. Given 150 feet of air equals 2.22 inch H2O, or inches of water gauge, in our example, which is for 60 degrees Fahrenheit ambient air at sea level. Picture illustrates the principle. The standard instrument which is used to take draft readings is the Magnehelic delta pressure gauge. However, if you wish to carry out a draft survey, it is possible to make some fairly good readings with nothing more complicated than a clear glass bottle, some water, and a length of clear plastic tubing. Fill the bottle with water, insert the plastic tube in the bottle. Attach the other open end of the plastic tube at the point where you wish to take the draft reading. The difference in the vertical height between the level of water in the bottle and the level of water drawn up in the tube will be your draft reading in inches of water gauge, as shown in picture. Draft induced by wind. Running with a positive pressure below the bottom row of convective tubes is potentially dangerous, especially if there is an appreciable quantity of sulfur in the fuel. The sulfur dioxide would then blow out of the sight ports and leak in the convective section. SO2 is a toxic gas. In some texts, it is advised to maintain a minimum safe draft of 0.05 inch H2O. However, there is a problem with this target. The problem is wind. Wind can create a variable draft of plus or minus 0.10 inch H2O or more. If the draft decreases, as the gusts of wind come and go, then the heater may go positive, and a personnel hazard is created. Thus, the minimum safe draft depends upon the variability of the wind. Not at grade, but the wind speed at the top of the stack. When draft decreases, due to a reduction in wind, airflow into the burners also decreases. If this causes the firebox to drop below the point of absolute combustion, then the heater will bog down and become flooded with fuel. That is, the heater will be caught in a positive feedback loop on the wrong side of the point of absolute combustion. Draft induced by density difference. Draft is mainly due to the density difference between the hot flue gas and the ambient air. Draft is also a function of the height of the stack. For example, density of cold air equals 0.070 pounds per cubic feet. Density of hot flue gas equals 0.030 pounds per cubic feet. Density difference equals 0.040 pounds per cubic feet. Stack height equal 100 feet. The calculated draft is then 0.040 pounds per cubic feet times 100 feet equals 4 pounds per square feet. To convert to inches of H2O, 4 pounds per square feet divided by 144 square inches per square feet times 28-inch H2O/PSI. Therefore, draft equals 0.80-inch H2O. The wind also creates 0.1 to 0.2 inches of water draft. Frictional losses in the stack tend to reduce draft. I usually ignore both factors, even though on occasion they may very well be significant. Draft induced by reduction in stack diameter. We were driving through some very rural and remote areas last year. The major crop was sugarcane. Every few miles there was a primitive process plant to produce raw sugar from the cane. The cane was crushed by electric motor-driven rollers to recover the sweet juice. The juice was then boiled down and partially evaporated, using the crushed cane as fuel. I noted that the top of the boiler chimney was about 1/3 of the diameter at the base of the chimney. The reason for this large reduction in chimney diameter is to help induce a draft by increasing velocity of the flue gas in the upper portions of the chimney. Neglecting frictional losses, the draft induced by increasing velocity due to the reduction in chimney cross-sectional area is as discussed in video on draw-off nozzle hydraulic section on nozzle exit loss calculation. Draft equals density divided by 62.3 times 0.186 times V2 power 2 minus V1 power 2, where density equals density of the flue gas in pounds per cubic feet. 62.3 equals the density of water, pounds per cubic feet. 0.186 equals the conversion factor used to convert kinetic energy into potential energy. V1 equals velocity, feet per second, in fat part of chimney. V2 equals velocity, feet per second, in thin part of chimney. Note that the 0.186 coefficient is based on the gravitational constant, 32.2 feet per square second. If the diameter of the chimney is reduced by 2/3, then the chimney cross-sectional area is reduced by 90%. Hence, if the velocity at the bottom of the chimney, V1, is 10 feet per second, then the velocity at the top of the chimney, V2, is 100 feet per second. Therefore, the draft due to the reduction in chimney diameter is 0.035 divided by 62.3 times 0.186 times 10,000 minus 100 equals 1.05 inches of water draft. The 0.035 is the density of the flue gas at 600 degrees Fahrenheit, assuming its molecular weight is the same as air. Caution, based on the roughness inside the stack, some or all of this draft may be lost due to friction. We asked the local guys running the boiler why they thought the top portion of their stack was so narrow. They simply answered, "This is the way it's always done. It is our tradition handed down for generations." Draft balancing. The air register and the stack damper are used together as a team to optimize the heater draft. Our aim in balancing the draft for a natural draft or a balanced draft heater is to maintain a small negative pressure of minus 0.1 inch of water, just below the shock tubes shown in picture, at the entrance to the convective section. At the same time, we must maintain enough air to operate on the good side of the point of absolute combustion. If we operate with a positive pressure in the firebox, although the burners may appear to operate normally, the hot flue gases will leak outward. This damages the roof arch supports and the steel structure so as to shorten the life of the heater. Flame impingement of the upper radiant tubes may also result from positive pressures. As we close the stack damper, the pressure at the convective section inlet will increase, that is, we will have less draft. This will reduce the rate of flue gas to the convective section, minimizing the rate of air in leakage to the convective section and the chances of afterburn occurring. However, if we close the stack damper too much, a positive pressure will develop at the convective section inlet, which we must avoid. Conversely, as we open the stack damper, the pressure at the convective section inlet will decrease, so that we have more draft. If we have too much draft, we will increase the risk of afterburn as we are increasing the rate of air in leakage in the convective section and stack. We adjust the draft with the stack damper and maintain the combustion air level by adjusting the air registers to accommodate the adjustments made on the stack damper. Evaluating fuel wastage due to air leaks. Convective section air leaks reduce the thermal efficiency of the heater by mixing cold ambient air with hot flue gas. The resulting energy debit may be expressed as follows. Delta F equals Ts dot times O2SO2C divided by 500 where delta F equals % heater fuel wasted through lost heat recovery in the convective section. Ts equals stack temperature, degree F. Tot equals ambient temperature, degree F. O2S equals % oxygen O2 in stack. O2C equals % oxygen in combustion zone, i.e., just below the shock tubes at the inlet to the convective section. Just for practice, let us suppose we have a stack temperature of 600 degrees Fahrenheit, ambient air is 100 degrees Fahrenheit, the convective section has 10% O2, and the firebox has 6% O2 measured just below the shock tubes. What percentage of fuel fired, delta F in our equation, is being wasted by cold air leaking into the convective section? Answer is delta F equals 10 to 6 times 600 minus 100, divided by 500 equals 4%. Minimizing fuel wastage due to air leaks. Suppose we now cut back on the combustion air by closing the air registers a little. The oxygen content in the firebox is now 3%. The oxygen in the convective section will also be reduced to, say, 9% oxygen. Notice how the difference between the firebox oxygen and convective section oxygen, which we refer to as DO2, has increased. It is now 6% O2. This is because the draft through the heater has increased, that is, the pressure is more negative, and more air is being sucked in through the holes or air leaks in the convective section. If we still had a stack temperature of 600 degrees Fahrenheit with ambient air at 100 degrees Fahrenheit, we would now be wasting 6% of the fuel fired. This is not a pleasing result, as we can see extra fuel will have to be burned in the firebox to offset the increased air in leakage. Suppose we put the air registers back as they were in pinch on the stack damper instead. So, let's suppose we restrict airflow via the stack damper until the firebox oxygen goes down from our base case value of 6 to 3%. The oxygen in the convective section will also be reduced to, say, 5%. In this case, we see that the DO2 is also much less, only 2%. This is because we now have less draft through the heater, that is, the pressure in the convective section increased and so has reduced the air in leakage rate. This also illustrates how the air leaks themselves vary in accordance with the combined operation of a stack damper and air register. Patching air leaks. To suppress afterburn and minimize energy losses caused by in-leakage of cold ambient air, any holes in the heater walls, convective section, ducts, and so on, should be patched. Also make sure that inspection ports are closed. Leaks can be detected on stream to a certain extent by visual inspection. Crumbling chalk dust or dropping a little baking powder past a suspected leak will pinpoint the leak. During a turnaround, a smoke test should be carried out as follows. 1. Close the stack damper. 2. Ignite colored smoke bombs or even old tires in the firebox. 3. Turn on the forced draft fan, if there is one, to assist the smoke. 4. Watch to see where the colored smoke emerges, as these points are the sources of the air leaks. Patch the leaks using heavy-duty aluminum tape, insulating mud, or silicone sealers, and weld up any loose sheet metal. Efficient air-fuel mixing. The function of a burner is to mix oxygen, in the form of air, with the fuel so that the fuel will burn more efficiently. Burners are available in a variety of different designs, all engineered with the intent to maximize air to fuel mixing efficiency. In more recent times, we have the added concern of also minimizing the formation of atmospheric pollutants. Fuel will burn at the end of a pipe with no burner at all, but the combustion will be far from efficient. Some burners are fitted with primary and secondary air registers, as is the premix burner shown in picture. Air entering through the primary air register mixes much more efficiently than does the air that enters through the secondary air registers. Thus, we should maximize the use of primary air, and we do this by gradually opening up the primary air register until the flame just begins to lift away from the burner tip. The remaining combustion air should be provided through the secondary air register. Optimizing excess air. The term optimizing excess air, as we have seen, does not refer to operation at some arbitrary oxygen level. Instead, consider the following in relation to your heater, and you will be optimizing excess air. Minimize fuel rate for a given heater outlet temperature or steam production in a boiler, then operate at 0.5 to 1% higher oxygen. Maximize primary air to burners, where burners have primary and secondary air. Adjust draft to minimize air-in leakage while maintaining a small negative pressure at the entrance to the convective section. Close openings to pilot lights, sight ports, and other holes around burners. Combustion air only mixes properly through the burner air register. When operating at reduced firing rates, shut down some burners if possible, as burners work more efficiently when operating close to their design capacity. Also remember to close air registers on idle burners. Minimize poor lateral air distribution in the firebox by adjusting air registers on individual burners. Having a low airflow in one part of the heater will lead to higher overall oxygen requirements. Keep burners clean. Plugged burner tips increase oxygen requirements. Maintain a regular burner cleaning program. Pay attention to the visual appearance of the firebox. Air preheaters. A typical air preheater will reduce the fuel required to liberate a given amount of heat by 10%. The debit for this improved thermal efficiency is a higher flame temperature and the possibility of overheating the radiant section. There is a clear advantage to fit an air preheater to a furnace when the firebox is running below a maximum firebox temperature. 3 types of air preheaters are in common use. Direct heat exchange between flue gas and air. Heat exchange via intermediate circulating oil. Heat exchange via massive heat transfer wheel, packed with metal baskets, Lundstrom type. The wheel type is subject to air leaks across the mechanical seals. This leakage is identified by increased oxygen content in the flue gas, low flue gas outlet temperature, and a greater temperature loss in the flue than rise in the air temperature across the preheater, as shown in picture. In general, air preheater leaks are a problem because they reduce the thermal efficiency of the air preheaters, may reduce combustion air so that it falls below that required for absolute combustion, resulting in destructive afterburn. Note that air preheaters themselves are often destroyed by afterburn. May cause the forced draft fan to operate at higher flows, requiring higher driver horsepower. All air preheaters are subject to corrosive attack caused by condensation of sulfur trioxide. At a 150 ppm sulfur in the fuel gas, operating experience shows that a minimum temperature of 350 to 400 degrees Fahrenheit minimizes corrosive attack. Uneven cooling in the preheater results in the need to keep the flue gas outlet temperature 50 to 100 degrees Fahrenheit above the calculated SO3 dew point. The flue gas outlet temperature can be increased by use of an air preheater airside bypass, or by increasing the excess air in the firebox. Preheater vibration. Air preheaters or any type of waste heat recovery device designed for horizontal flow across vertical tubes may be subject to vibration produced by the velocity of gas across the tube banks. The velocity produces a vortex shedding wave pattern that could correspond to the natural harmonic frequency of the tube bank. If the natural harmonic frequency is reached, excessive vibration of the tubes will occur. Redesign of the internal baffle system by inserting dummy baffles can stop the vibration. Vibrations in fired equipment and afterburn. Balanced draft or induced draft furnaces and boilers are intended to be operated with a small negative pressure, Ca-0.1 inch H2O, just below the first row of convective tubes, that is, just below the shock tubes. If we operate such a piece of equipment with a severe shortage of air in the firebox and massive air and leakage in the convective section, it may sometimes experience thumping, puffing, or vibration. Take a look at my sketch of a puffing boiler, shown in picture. It is operating with perhaps a little too much draft, but look at the firebox oxygen. It is only 0.6%. However, the oxygen content of the flue gas steadily increases to 3.1% at the outlet from the convective section. This boiler has a tremendous amount of air leaking into the convective section. Perhaps someone is operating it on the basis of that 3.1% oxygen to the stack, without checking the firebox conditions. Very foolish, as I hope you will now agree. This boiler is puffing, too. Perhaps I should have shown its convective section walls alternatively convex and concave, but instead I have just entitled it the puffing boiler. Here is what actually causes the puffing, vibrating, or thumping. The fuel gas is not properly combusted at the burners, so partially combusted hydrocarbons and perhaps some totally unburned fuel pass up into the convective section with the flue gas. The convective section, as shown in picture, is under negative pressure, so air leaks in and mixes with the hot unburned hydrocarbons, which then reignite. Thus, we have afterburn in the convective section. The heat of the fire in the convective section expands in the flue gases, causing a positive pressure in the convective section, which stops the air leaks. After some period of time, the fire in the convective section has consumed all the tramp air and is extinguished. The convective section flue gases then cool and shrink, re-establishing a negative pressure as before, and, as before, air leaks into the convective section and the hot, unburned hydrocarbons from the firebox mix with that tramp air and reignite in the convective section. This cycle of events will continue, except each time the ambient hydrocarbons ignite in the convective section and the pressure changes from negative to positive, the leaks will increase in size as the boiler fabric is shaken. If the airflow to the firebox becomes very severely low, then one or more of the burners may be extinguished through lack of oxygen. If the fuel is then left to flow unchecked, it will build up in the firebox until eventually enough tramp air has been sucked into the firebox, at which point the extinguished burners may be reignited by the heat left in the refractory walls, causing a minor explosion or a detonation as it ignites. The magnitude of the explosion depends on the degree of oxygen starvation. If anything like this is happening to your fired equipment, open up the air registers, get more air into the firebox, and patch the leaks. Lighting burners. Before lighting burners in a piece of fired equipment that has been idle or offline for any time or whose burners have become extinguished during operation, it is vital to first purge the firebox of hydrocarbons and combustibles or explosive mixtures. Here is a method as outlined to me by a prominent burner manufacturing company. 1A. If the furnace or boiler has a forced draft fan, open the dampers and displace 5 volumes of air. 1B. If the furnace or boiler is natural draft, open the air register and stack damper and wait for 5 to 10 minutes. 2. Check the firebox with a hydrocarbon detector. The plant's fire station will usually have one of these and someone trained in its use. Pay particular attention to stagnant areas of the firebox, as fuel gas valves tend to leak through burners and gases build up in areas of low airflow. Look for unburned gas and explosive mixtures. If you detect any such fuel or explosive mixtures, repeat step 1A or 1B, then test again with the hydrocarbon detector. Continue this process until the firebox is purged of all combustible or explosive material. 3. Light the pilot lights. 4. Light the burners using pilot lights. Please note that it is not only bad practice but extremely dangerous to light main burners without the use of a properly installed pilot light. Butane torches, fireworks, torches consisting of gasoline-soaked rags on sticks, or residual heat in the furnace refractory do not provide a safe alternative to a properly installed pilot light. Please also note that fired equipment either without burner pilot lights or with extinguished burner pilot lights have been known to explode during operation, as the pilots, when lit, do provide some means of safely relighting or keeping main burners alight. An explosive mixture in the firebox is indicated for methane, that is, natural gas, when the methane content is between 5% and 15%. When the firebox methane content is below 5%, the air-fuel mixture is too lean to combust. When the methane content is above 15%, the mixture is too rich to combust. The comparable values for hydrogen are 4%, too lean, and 75%, too rich. This suggests that refinery fuel gas, which may contain 5 to 50% hydrogen, can explode much more readily than natural gas. The presence of H2 in fuel gas is a strong argument, then, for connecting pilot lights to natural gas, which is very low in H2. We have had several sad experiences of losing coworkers due to firebox explosions. Always, the deaths could have been avoided if the pilots had been lighted first. For example, a survivor will say, "We tried to light the pilot lights first, but they wouldn't light off. It isn't our fault that HDS heater blew itself up." Okay. It's not your fault. Some idiot connected the pilots to dirty fuel gas, rather than natural gas. But why didn't you clean out the little spud inside the pilot light? It only needs a crescent wrench to do the job in 2 minutes. That isn't our job, the operators replied. Okay. But if you can't get the pilot lit, then don't open the gas to the main burner. Well, how are we going to start up the HDS without H3? It's simple, guys. If you can't run a unit safely, then don't run the unit. This was a pretty accurate rendition of a discussion with two operators at the Tenneco oil refinery in Chalmette, Louisiana, in 1984. Today, burner manufacturers have access to all kinds of designs for pilot lights, to fit all shapes and sizes of burners and burner ports and draft systems, from the smallest breeze to gale force winds. There is no longer any excuse to operate without pilot lights installed and working. Oil burners. In the United States, oil firing is uncommon. In Europe, it's pretty standard. Most oil-fired burners use atomizing steam to produce a large surface area of the oil exposed to the combustion air. In the steam atomizer shown in picture, jets of oil under pressure meet the spinning jets of steam under pressure in the mixing chamber. A mist of oil and steam is discharged into the furnace. The pressure drop of the oil through both the oil orifices of the tangential slots is typically 10 to 30 psi, 0.5 to 2.0 bar. In general, an oil-fired burner uses a higher percent of excess air, as it's more difficult to mix air with liquid fuel than with gaseous fuel. The fuel oil flows from a circulating hot oil system kept at several hundred degrees F, depending on what is being burned. In most refineries, vis breaker or vacuum tower bottoms provide the fuel oil, which is circulated at about 500 degrees Fahrenheit. Burner tip plugging of the oil orifices shown in picture is a routine problem. The most serious problem is loss of fuel oil circulation in case of an electrical power failure. The fuel oil can then solidify in the circulating system and in the burners themselves. For example, vacuum tower vis breaker bottoms can solidify at 300 degrees Fahrenheit. Heat balancing. Let us finally look at a situation where one might wish to transfer heat duty from the firebox to the radiant section. At the beginning of the discussion on air preheaters earlier in this video, we noted how fitting an air preheater to an existing furnace would increase the flame temperature and possibly overheat the firebox. Suppose a fired heater in an oil refinery, in service to heat crude oil, is fitted with a new air preheater. The firebox was running hot before the air preheater was installed, but the management was convinced that the installation of the air preheater would allow them to heat more crude oil. When the heater with its new air preheater came back online, the following changes were noted. Fuel gas consumption was down by 10%, for the same heat absorbed as before the revamp. The firebox, which was hot before the revamp, was now hotter, even at the original crude oil flow rate. Thus, rather than running more crude, operations personnel had to cut back the crude rate to maintain satisfactory firebox conditions. crude oil side convection outlet temperatures were lower. Here is what happened. Preheating the air by 300 degrees Fahrenheit had raised the burner flame temperature by 300 degrees Fahrenheit. The hotter flames then radiated more heat per pound of fuel consumed, and as a result, the firebox became much hotter. The same factor that reduces fuel consumption in the radiant section also reduced the flow of flue gas to the convective section, thus reducing the convective section outlet temperature. So, what can we do to actually run more crude, especially as there is no bypass around this new air preheater? The answer, of course, is to allow more air into the firebox and thus generate more flue gas. The firebox oxygen was increased from 3 to 6%, which reduced the firebox temperature to its pre-revamped state. This, in turn, increased the pounds of flue gas flowing through the convective section and increased the heat absorbed in the convective section. The increased combustion airflow was needed not for combustion, but to transfer heat from the radiant section, firebox, to the convective section. This is what we call heat balancing. In this situation, oxygen requirements to reach absolute combustion become irrelevant as we are now operating with a very plentiful supply of oxygen. Lack of air affects draft and combustion. Normally, opening the air registers at the base of a heater reduces draft, that is, increases pressure below the bottom row of convective tubes. This happens because the extra combustion air creates more flue gas, which results in an increased increment P across the convective section tubes and the stack damper. However, if the heater is operating in an oxygen-deficient environment, or it is running below the point of absolute combustion, draft will likely increase as the air registers are opened. We saw this happen recently. When the air supply to the burners was increased, the flame appearance changed from dull orange to a bright bluish yellow. The firebox became noticeably hotter. We assumed, but failed to check, that the stack also became hotter. A hotter stack reduces the density of the flue gas, and that will always increase draft. The airflow was normally restricted to meet an arbitrary, and apparently excessively low O2 target in the stack. The conclusion, then, is that if opening air registers increased draft, the heater had been operating below the point of absolute combustion. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.